All right, why don't we go ahead and get started? So welcome back everybody to EE240. So just a couple of sort of quick administrative kind of things. I've posted the first phase of the project up yesterday, so you guys should go and sort of take a look at that. Just as a reminder, the projects will be done in pairs, so you should grab a partner and make sure you've got that all set. So this is starting even from this very first phase, although once you look at it, you'll see that this first phase is really a lot more like a homework. So it's a little bit, sort of smaller scale than really what the final project will be. So it really shouldn't take, sort of too much time. That's not to say it shouldn't get started early, but this one is sort of a little bit more scaled, really just to kind of get you an introduction into the overall area that we'll be looking at, which hopefully we'll start talking about today. We probably won't have covered sort of all of the material you need to really get going on the project by the end of today. We should do that by sort of the beginning of class on Thursday, but definitely go ahead and grab that and take a look. At least some of the initial stuff, just to give you an idea sort of what direction we're taking, should be clear. And as I'll sort of cover a little bit later on, one of the main points of doing this project is you're going to see that there's going to be several different blocks that you're going to be looking at. And as I sort of mentioned at the very beginning of the class, the reason I want to do that is because I want to really drive home the point that a lot of analog design is not just about taking one block and building it to meet a whole bunch of specs, but really understanding how do different things trade off with each other. Because a lot of times, you'll get a set of specs and somebody will tell you to go and build them, but actually if you just sort of traded things off between a couple of different blocks in a slightly different way, you'd end up with a much, much better overall solution. So that's really kind of our way of starting to take a look at some of that stuff. Obviously we have some more material to cover before we get there, so unless there's any kind of questions on either homework or project or stuff we've covered so far, which I guess is now, that's your opportunity. So any questions? Okay, so with that, why don't we just go ahead and dive back in. So last time we were sort of talking about multi-stage amplifiers, specifically two-stage amplifiers. We'd kind of gone through and discussed all the different stability considerations. And where we basically ended up was sort of looking at using nulling resistors to get around some of the issues introduced by using the Miller compensation technique. So of course, just to remind everybody, what we were talking about there was if we have a two-stage amplifier and we just use, of course, a simple Miller capacitance, then a lot of times what you end up with is that feed-forward zero there actually ending up close to somewhere that you care about it from a stability standpoint. So we said that we could essentially add a resistor in there to try and null that feed-forward zero out. And then we talked a little bit about just how you'd actually implement that resistor, given that you really want that RZ there to somehow be related to the 1/GM of that second stage. So there was some issues there. We said there's some sort of clever techniques you could use. But what I want to just briefly cover now is take a look at what if we could actually do this Miller compensation. In other words, add in this compensation cap right here, but do it in a way that didn't have a feed-forward zero, so we don't have to worry about its impact on our overall stability. Okay? So sounds like maybe this is hard to do, but conceptually it's actually quite simple. So if you guys remember, the whole reason why this feed-forward zero was a problem was essentially because basically when we take current and go straight from this point to that point, the gain from here to here would be positive. Whereas if we went through the actual amplifier, it would have been negative. That was kind of the whole source of this problem. Well, so what if we could take this thing and rather than allowing current to flow this way, what if we only allowed it to flow that way? In other words, we made the feedback that this Miller compensation is doing unilateral, right? So that we could only really make it feedback and there's no feed forward at all. Well, if you could do that, then indeed, the sign of the gain would always be positive. And so you wouldn't have this sort of feed-forward zero or right half-plane zero issue. So the way to do that is actually conceptually pretty easy. So imagine that I just have my two stages, and then I have my Miller capacitance on the second stage. Well, guess what? If I just put like a little amplifier there, and actually I'll flip the ordering just so that it will be more clear how I've done it. Imagine I just put a little amplifier right there. Okay? So that amplifier obviously likes to look at this input and drive that output. So again, conceptually, this should make it so that to the extent that this amplifier is a good amplifier, I should only be taking signals from this output over here and feeding them back, but not going the other direction, right? Okay, so this sounds good, and so actually let's take a look at how we might really implement that. So by the way, the guy who came up with this was a person named Ahuja. This was in JSSC, I believe, in December 1983. Okay, so if you're interested, you can go and sort of look up the paper. But this is the basic structure that he used. So this first stage here, that's just sort of a differential OTA. He converted it to single-ended. Don't worry about that. So this is really just the first stage, OTA. This is really the second stage, OTA, right here. And then this piece right here is really just that amplifier. Okay? Now, he built this as a common gate amplifier, because if you sort of pay attention to the signs of things, you want this feedback here, and I'll do it sort of, I'll be careful. You know, if both of those have negative gain, you really want that feedback there to have positive gain. Right? If it doesn't have positive gain, then actually you'd be creating a positive feedback internally in this structure, which obviously you don't want. Okay? So if you want positive gain, and obviously you don't want to do that with multiple different stages, that's why he used this sort of common gate amplifier right here. Okay, so the idea is if there's some wiggle at the output right there, that couples onto the source of this PMOS transistor, and then obviously feeds back onto the gate right here. Okay? So from the standpoint of the Miller capacitor, looks basically the same. It's sort of doing exactly the effect that we had wanted. Okay? So indeed, you can do it. It's nice because it has no red half plane 0. Turns out this never really caught on, which is probably why you didn't learn about it before. Okay? And the reason is, it turns out this actually costs you quite a bit of power. So the way to see that is actually sort of fairly straightforward. And by the way, the reason it actually ends up costing you power is largely having to do with the fact that essentially this current right here, if you hit this amplifier really hard, has to slew the Miller capacitance. Okay? So again, the way to see that is just imagine we have the following situation. So imagine that the differential input is such that, you know, I push this thing really, really hard in the direction of the two arrows that I just said. So in minus is very large and in plus is very small. Okay? So that essentially all of this bias current is going to flow through there. Well, if we do that, this is going to go up to a pretty high voltage, right? In other words, this transistor right there is going to get cut off, right? Well, if that transistor right there is cut off, then now the only current we have available to charge up the Miller capacitor is I2, right? Because remember, if I have a current source in one branch of a circuit, the overall current has to be that. So it doesn't matter what this thing is doing. This is what's going to limit the current flowing through that capacitor. Okay? Well, if this is what limits the current flowing through that capacitor, and I need to have good settling behavior, then unfortunately that means this current right here has to be fairly substantial. And remember, the whole point of doing this was that we just wanted to get higher gain, but we still wanted all of our performance and everything to really be set by the GM of the input stage, or really the bias current of the input stage. Well, so now that I've done this, unfortunately, again, I have to spend some real power on that I2 right there. So even though it works, it's a little bit easier. You don't have to worry about the right half plane 0. Basically, people never used it because it's just too expensive from a power standpoint. Okay? So really it's a nice idea, but the issue here was that we sort of had to add some extra bias current into this thing to make it sort of work, or really to get the sort of performance that we wanted. So it turns out there's actually another way you can do this so-called cascode compensation. By the way, you'll see why I call it cascode compensation in a second. This particular version was from a guy named Ribner. This was also, I believe, in 83, 84 or so. So the basic idea here is actually pretty simple. So let's just say, and I'm only going to draw the single-ended version here, but you can imagine I could do this with a differential as well. So let's say that's my input. Let's say I have just some bias voltage right here. So I have a cascoded first stage. And actually, that's not a resistor here. Sorry. I'll draw that as a current source. So this is just my sort of OTA for the first stage. Okay, and so let's say this would have been my normal, like, two-stage OTA, right? So normally, if I was going to do Miller compensation, I would add the capacitor like this, right? Well, so the idea this Ribner guy had was to say, well, okay, the way I want to make things unilateral is somehow I'm sort of like adding in some common gate amplifier that's going to grab the signals off the feedback cap, right? And somehow it's going to unilateralize things. Well, remember, a Cascode device is kind of like a common gate amplifier, right? So his idea was, instead of putting the Miller comp cap where I drew it in blue, why don't we do this? Okay, so in other words, why don't we take the CC from the output and tie it back into the source of the Cascode there, rather than into the drain? So what's conceptually nice about this now is, basically, I'm not spending any extra bias current, really, right? Because I needed this Cascode, presumably anyways, to get the gain that I wanted to get. Okay, so at least in theory, I'm not spending any extra bias current because of that. Okay, so by the way, just in case it's not clear how this thing works, remember the whole point is we want signals to flow that way, but not the other way. And so the way that happens is, if you think about the input current, as long as the 1/GM of this Cascode is basically low enough impedance, then all of that current should flow into the Cascode. None of it should go through that CC over there, right? Now, turns out this also was not exactly very popular, which is why you probably haven't learned about it before. So, any ideas why this is not super popular? You know, what's the sort of annoying thing about all this? Or annoying things, I should say. What do you guys think?
Changes the third pole from that.
Yeah, exactly. Actually, so what happens here is, remember, anytime you do this thing, you're going to pick up a third pole from that Cascode. Well, now that third pole is very intimately tied to your overall compensation network, right? So in other words, if you throw in this CC, that's going to muck around with the third pole that comes from the Cascode. So actually, the biggest reason this didn't catch on is because it's a major pain in the ass to design. Okay, because it's just really hard to go through all those third-order equations and figure out exactly where you want to place all the stuff that you want to place. It's not to say you can't do it, it's just kind of a pain in the ass. Okay? So that's actually the main reason why this wasn't super popular, is essentially what you now have is really intrinsically a third-order system. And again, basically by playing with that CC, you're playing with multiple things at the same time. So it just gets a lot harder to figure out what's the right way of actually designing that amplifier. The other thing is, which is just sort of a side note, remember, anytime somebody draws a capacitor like this, you should remember there's no such thing as a perfect floating capacitor. There's always the so-called bottom plate, which really means there's both parasitics on the top and bottom plates. Well, and so notice if I'm adding some parasitics onto that Cascode node there, that's kind of bad news, right? We said we really want to minimize the parasitics there just to make sure that the bandwidth of that thing is high enough, to make sure that it doesn't introduce extra noise, and so on and so forth. Okay? Does this kind of make sense to people, or? Okay, so again, sort of interesting idea, never really caught on. So most of the time, what you're actually going to do is use nulling resistors. Okay, so now that we sort of beat stability to death, the last thing I want to talk, actually maybe there's one other thing after that, but the second to last thing I want to talk about in terms of multi-stage amplifiers is just how to analyze the noise for this thing. Because again, if you want to use it, obviously you need to know not only sort of stability and gain and bandwidth, but what's the noise performance of the amplifier going to be. So the bad news, quote unquote, is that, you know, if I build a real multi-stage amplifier, I could pretty easily have something like 30 or 40 transistors in that thing. And so clearly you don't want to sit there and start writing small signal equations for every single last transistor there, because you'll just be sitting there and doing math for a long, long time, right? So what we obviously want is some sort of a simplified model. So what I'm going to do is actually, again, sort of go back to our very simple model for the two-stage amplifier, which of course just looks kind of like we've been drawing multiple times already. Just essentially like two common source stages. Okay, and for now I'm going to assume that, let's not even worry about the nulling resistor. Let's assume that I can actually get the design that just looks like this to work the way I want it to work. Okay? Okay, So now, when I'm building this thing, I'm typically going to be using the amplifier in some sort of feedback loop. For example, like our capacitive feedback loop. So I'm just going to go ahead and assume that we're doing that here as well. So I've got some V out right here. And of course, I'm going to have some CL right here. Let's just go ahead and label that CC. Okay? So if I'm going to use this in a capacitive feedback loop, then that means that what's going to show up back at the gate of the input over there is minus F, F just being our feedback factor, times V out. Okay? Okay, so this is definitely a simplified model. And as we'll see in a second, this is going to be pretty useful for us to actually do some noise calculations with. So as usual, the first thing you do if you want to do a noise calculation is just sort of draw the small signal model for this thing. So let's go ahead and do that. So again, nothing sort of too complicated there. So I basically have F times GM1 times V out from that first stage. Then I'm going to have essentially a CC right here. So again, I'm going to ignore all the ROs and everything like that, like we typically do for noise calculations. Then if we call this, let's say, V1 right here, I'm going to have GM2 times V1. And then I'm going to have my CL at the output right there. And then V out. Okay? Okay, so I obviously didn't draw the noise sources in just yet. I'll do that in 1 second. But already you can actually kind of see that this gets a little bit painful if you really include the Miller cap this way. Because that feed forward term, I mean, we can deal with it, but it just kind of gets annoying to come up with very simple and useful expressions if you do it this way. So I'm going to simplify this thing even one more time. Okay? So by the way, actually, you guys can probably guess at this point. What do you guys think is going to be the, let's say, approximation I'm going to use to try and simplify this even one more time? What did you guys learn about in 140?
The DC gain times CC?
Yeah, basically, right? You sort of learned like the Miller approximation, right? Where you sort of split that cap onto the two sides. I'm going to do something very similar. Okay, so I'm basically going to say, I'm going to assume that the feedback is essentially unilateral. So I don't want to deal with a feed forward 0. Okay? So the way I'm going to do that is something like the following. So basically I'm just going to take this thing and essentially split it into two stages. And now I'm going to add the noise sources in. Okay? So I've still got my GM1 times F times V out right here. I'm of course going to have some noise current, let's just call that IN1, coming from that GM stage. This is still going to be V1 right here. I'm going to have my Miller coupling cap. And so now to unilateralize the feedback, I'm just going to say that, pretend as if I'm essentially just driving V out directly. Okay, so what I've essentially done here is I've made it so that the current coming from that GM can't affect V out, but V out can feed back onto this first stage. Okay? So I've effectively just unilateralized the feedback. In other words, I've made it only go in one direction. So once I've done that, of course, I can now draw the second stage, and this is, again, where we sort of invoke our normal Miller approximation. So we say there's just a CC to ground. We have our GM2 times V1, right? Actually, we'll have, of course, the noise current coming from that GM stage. And then finally, we'll just have our load cap, right? Okay, so this is basically actually the small signal model I'm going to work with. So now, you can take this model, you can write just essentially KCL or KVL at a couple of points there. And you can pretty quickly come up with just, sort of what's the equations that you'd be working with. So because it's not particularly informative, I'm not going to do that. But if you're interested, come bug me later. I can tell you exactly which two equations to write. But essentially, once you have this model, what you can pretty quickly do is come up with the following expression here. Okay, so it basically tells you that the output voltage as a function of the two noise currents is just related to 1 over F GM1, which again kind of makes sense since we've tied this thing up almost like a diode, times some filtering transfer function here. Okay, that's related to the dynamics of this whole thing, times this IN1 minus IN2 times some other filter inside of here. Okay? So again, you can come up with this pretty easily. This is what the sort of coefficients in this transfer function are. Nothing too magic there. The only sort of thing, to notice is that that term right there is kind of like the resistance. This is just essentially the filtering. And then this is just the noise from the first stage, noise from the second stage. Okay? So again, I trust you that you can do this math at home, so I'm not going to spend a lot of time on it. But if you do the sort of the integration of that, again, following our standard procedure for how you deal with noise, then what you'll quickly find is that the total noise at the output basically boils down to something that looks like this. Okay? So I have something that looks like kT over cc times gamma over f plus kT over cc plus cl times gamma. Okay? So this is actually kind of interesting. I can rearrange this slightly. What I want to do is I just want to take this term over here, which, by the way, just in case it's not clear, this is the noise from the first stage, and that's the noise from the second stage. Okay? So what I want to do now is I'm going to rewrite this slightly, just to make it so that the total noise is the noise from the first stage times 1 plus some scale factor there. Okay? So literally all I did was just pull this out to get that expression right there. And actually what you see is actually something sort of pretty interesting. So this term right here, which again is just really representing the noise from the second stage, is guaranteed to be less than 1, unless I have like some active feedback or something like that, right? Because cc over cc plus cl, clearly that's less than 1. And usually our feedback factor is also less than 1, right? In other words, roughly speaking, the total noise is just going to be kT over cc times gamma over f. Okay? So notice this actually looks deceptively similar to the noise we got from a single stage amplifier. There's just one really big difference. So in a normal single stage amplifier, the cap that would have been setting our noise would have been CL. In other words, the output cap. Whereas now, because we use this Miller compensation technique, it's actually CC that's going to be setting our noise. Okay? So this is kind of interesting, or I should say kind of intuitively makes some sense. Because remember, in the single stage amplifier, what's basically setting the bandwidth at the output is CL, right? But in our multi-stage amplifier here, because we've used Miller compensation, it's actually CC that's setting our bandwidth, right? So if CC is the thing that's setting your bandwidth, it makes perfect sense that that's also what's going to set your noise. Okay? So again, the whole reason I went through this exercise is just to give you now, again, you have a very simple expression that tells you what's the noise performance for this multi-stage amplifier as well. Okay, and you can see it's kT over cc, which is, again, kind of good news because you know what you can do. You know how to design that cc to basically get a certain settling time, to get a certain noise performance, and so on and so forth. So you can actually go and take that amplifier design procedure that we spent a lot of time developing and pretty straightforwardly extend it to do a multi-stage amplifier instead. Okay? Does this sort of make sense to everybody? Or? Okay, so just one last sort of quick, let's say, brain teaser, so to speak, which is going to be related to using multi-stage amplifiers. Okay? So I'm just going to go ahead and sort of draw a multi-stage amplifier design, and kind of this brain teaser is, of course, going to be related to just how do you deal with the common mode feedback for something like this. Oh, sorry, actually let me draw that with real transistors. Okay, so let's say I have some sort of telescopic first stage. Okay, so something that looks like this. And again, I want to do a multi-stage amplifier just to get some additional gain out of this thing. So let's say there's some bias right here. Okay, and so let's say that obviously since the biasing works out much better than some of the conceptual designs I showed before, typically you'd want to use a PMOS for the second stage over here. And let's say I really do tie it up the way I've shown right there. So it's sort of, the second stage is now going to be pseudo differential. Okay, and then I'm going to take, again, I'm just going to have some current sources to bias this thing right here. And so now, just because it's sort of convenient, I'm going to tie the bias for all these current sources together. Because, hey, they're all just NMOS current sources, right? So why not just use them all together? And now I can say something like, well, okay, so my final output is over here. So why don't I just use that one final output, basically sense the common mode over there, and tie the feedback loop through that. So as an example, I'll do something like, and again, I'm going to draw resistive feedback here just because I'm lazy, but you might actually do this with capacitive feedback. So let's say I do something like that. Okay? So this is, let's say, some desired nominal common mode voltage. Okay, so now here's going to come the brain teaser. So conceptually, all this looks just fine, right? I'm sensing my common mode output voltage over here, and I'm forcing it, or I'm controlling it by adjusting this knob of bias current right here. So now, what sign should I put on the feedback of this amplifier? In other words, should it be, and I'll draw it in two different colors, should it be plus minus like this, or should it be minus plus like that? What do you guys think? By the way, there may not be one right answer, so. So what do you guys think? What's going to happen here?
The red one?
It's the red one. Okay, why do you say it's the red one?
Because if you increase the output voltage increases, the NMOS current source will, the current will reduce, which will cause the...
Okay, so let's say that this common mode voltage, and I guess we'll do it in red just to be consistent with the colors. So let's say that that output common mode voltage goes up, like you said. So you just said if I do the red one, then this will go down. That's right. Okay. So then what will happen over here?
So the first stage common mode will go up.
Ah, okay. So you're already more sophisticated. So let's do the simple thing first. So if this goes down, what will these guys do?
Drive the voltage up.
Yeah, those will push the voltage up, right?
Yeah.
So I'll put that on both sides right there. Okay, but is anything else happening? And somebody other than Shiva, I guess? Anything else happening?
Pass through the first stage.
Yeah, you got to pass through the first stage too, right? So this will go up, which will mean that both of these will go up, which means that those PMOSs will make this go down. Okay, so now we have some fun, because we have both positive feedback and negative feedback, right? So now, if we want this thing to be stable, what better be the case? So let's just label these things. Let's call this, I don't know, AVN times whatever VCM error, which is going to be, let's say, over here. And let's call this thing over here AVP times VCM error. So if we want this whole thing to be stable, what better be the case? What has to be true about sort of these feedback loops?
AVN have to be greater than AVP.
Yeah, exactly. Better be the case that AVN is greater than AVP. Right? Because if it isn't, then we actually have net positive feedback, and the whole thing will be unstable. Right? Okay, so now, and again, somebody other than Shiva, for this particular design, do you guys think that AVN is greater than AVP or not? Who thinks AVN is greater than AVP? 3, 4, 5 or so, 6 brave souls. Okay. Who thinks AVP is greater than AVN?
AVP on the bottom.
Because I just labeled AVP as being the positive feedback loop,
positive.
and AVN is the negative feedback loop. Yeah, you're right that it's flipped from the signs of the amplifier, but yeah.
I thought it was PMOS, NMOS.
Right. Okay. So who thinks AVP is greater than AVN? So 6-0. Okay. So let's see. Maybe we can tease it out of somebody. So somebody who said that AVN is greater than AVP. Why is that? Why do you think that? I tend to agree with you, by the way, so.
It passed through more gain stages.
Yeah, right? So basically, this AVN over here, it gets gained from this point to that point. Okay, there's not really any gain from here to here, because that's just kind of almost a cascode, right? But so it gets gained up from here to here. It goes through there. Now it goes through this PMOS gain stage as well, and then shows up at the output, right? Whereas from there to there, all you get is just the gain of these devices. Okay, so most likely, this indeed is the larger gain path. Okay? Now, by the way, I can't really guarantee that, because I could have come up with some perverse sizing that didn't exactly do it, but most likely that's actually the case. But actually what this is really kind of getting at is, don't forget, anytime you have common mode, you have to be really careful with how you tie those loops up. Because if you're not sort of thinking about it the right way, or just not thinking about it carefully, I guess I should say, you could very easily end up with some sort of positive feedback loop that you didn't intend. Okay? So, by the way, other than doing what we said, walking through this whole loop analysis and things like that, any idea what we could do that would be a little bit better to actually sort of make this whole thing work more cleanly? Or to avoid some of these?
Bias the current separately for first and second.
Ah, okay. So what you're basically saying is, why don't we just break this darn feedback loop? And again, I'll do that in a different color. Maybe what we should really do is just not connect those currents together. Maybe we should have separate feedback loops for each one of those. All right, so as an example, you could have one common mode feedback loop, and I'm not going to draw the whole thing, but you could have one common mode feedback loop for the first stage, and a separate common mode feedback loop for the second stage, right? That's a pretty reasonable idea, because that's much more clear, right? And then you're actually controlling the common mode on each individual stage. Okay, any other thoughts for something that you might do that, well, I don't know if it necessarily solves the problem, but makes things a little bit, let's say, easier to analyze?
You can tweak the PMOS sources of the first stage.
Ah, okay. So basically, you could do something like add a current source up there, right? So that instead of having a pseudo differential design right there, you actually have a fully differential design. Why does this help, by the way? What's sort of good news about doing that? Why in general do you add current sources onto things?
Differential mode?
Okay, well, differential mode versus what?
Common mode.
Right, okay, so what's the common mode gain of something like this? Yeah, it's supposed to be 0, right? It's supposed to be small, because this current source is supposed to just throw away all the common mode, right? So by doing something like this, by the way, if I really did add that current source in, which way would I choose these? Red or blue? Blue, right? Because I just got rid of that whole negative feedback loop from the other side. Okay? Okay, good. So like I said, the key point here was really just that, when you do multi-stage amplifiers, as soon as you got multiple stages, you can't just worry about the stability of the differential mode. You got to worry about the common mode as well. Okay, and a lot of times that can involve a lot more subtle issues than what you might at first expect. Okay? But in particular, the other thing I want to remind you is that anytime you end up with these multiple feedback loops, or one's positive and one's negative, which by the way we'll see happening a whole lot more in a second, you got to make sure the negative feedback loop actually wins. Okay? Yeah.
So if you add in the current source, you eat into the swing.
That's true.
Right?
That's true. So no free lunch, right? You're going to eat into the swing. So indeed, you may actually just want to do the thing we had discussed before, which is separate the common mode feedback for the two stages. It's a good question. Any other questions on this? Or yeah.
Can you just have one feedback loop? I mean, like.
Say that again?
Can you just have one common mode feedback loop?
as we've drawn it here.
I mean, like, have the second stage current sources to be separate.
Yeah, no, I think that's what we sort of had drawn in black before, of basically separating the two loops. So you have one column mode feedback loop for the first stage, and a second column mode feedback loop for the second stage.
No, what I'm saying is, like, don't have a common mode feedback for the second stage at all.
So how are you going to control the column mode then?
Because the first stage will fix the second stage common mode, right?
Says who? Right? These are both high impedance. So what if there's just an ever so small mismatch between, you know, this mirroring ratio or that mirroring ratio? If this is a high gain stage, who knows what the common mode is, right? Because remember, anytime you do, although in Spice it's usually perfectly happy to tell you that this works, anytime you do something like that, you do not know where that common mode is actually sitting. You may think you do, but trust me, you don't. Right? Because if the output impedance is high, there's no feedback, there's no nothing that's forcing it to be there. Right? I just have two current sources, and the two current sources, I tied them together, so the voltage, at least if they were really current sources, could be whatever it wants. Right? Does that make sense? Or?
This is saying that the first stage's common mode
Yeah.
affects the second stage's common mode.
Yeah, it's true that, you know, the way I drew it before without this current source on the top,
Right.
it's true that it does affect it, right? But if I didn't have any feedback onto this point, there's no reason why when I control this common mode, I'll get exactly the same common mode over there, right? Because again, the ROs are a little bit different. The mirroring ratio could be slightly off, right? And if I have a gain of, let's say, 100 through here, all it takes is 10-ish millivolts or so, and I'm out of the rail, right?
So when we have both positive and negative feedback, how careful do we need to be about the bandwidth?
Okay, so certainly this had better be true at DC, but not only that, it had better be true across a wide range of frequencies, right? Because if there's some frequency where the positive feedback actually wins, you could indeed have something that just likes to oscillate at that particular frequency. So in fact, you'd have to do like the complete loop transfer analysis, where essentially what you'd have is T1 of S minus T2 of S, right? So you'd have to look at basically the, let's say, phase margin of that whole thing right there, which is fun, but can be done. It's another good question. Any other questions on this, or? Okay, so unless there's more questions, let's actually go ahead and move on to the next sort of set of notes here. So the last sort of major topic that I want to cover before we really dive into the material that's really directly driving at our project is essentially going to be biasing and references. Okay? So the reason I'm going to spend some time on this is that although, you know, maybe in your research or in some places like in this class, I'm nice to you and we give you some sort of bias current or bias voltage or something like that. Of course, in reality, 90x% of the time, nobody gives you that for free. You got to come up with some way of basically biasing up your circuit using only stuff that you yourself built on the chip. Okay? Now, there are a bazillion different, you know, sort of bias or reference circuits that people have come up with in the literature. Okay? And there's all kinds of different sort of specs that people talk about. So things like how much power does it burn, how accurate is it, how much power supply does it reject, what's the output impedance, and so on and so forth. But there's really kind of one important thing to keep in mind, which is going to drive us through sort of looking at a lot of the different circuits here. Okay? So most of the bias circuits, they're called some sort of constant X, where X may be resistance, it may be current, it may be voltage, it may be any one of a number of other things. Okay? So really the key thing to keep in mind with any bias circuit that you may end up building is to ask yourself, what is it that you actually want to be constant? In other words, what is the X that you really actually care about? Okay? So just to make that clear, let's just go through sort of an example. So a lot of times if you look in like books or things like that, or even actually the way that we have been talking about things in class, we said that somehow magically somebody gave you some constant current, let's say IB, and then you just use the current mirror to copy that over. to, let's say, some amplifier, which, let's just pretend we have some very simple resistively loaded amplifier like this. Okay? So this is kind of our classic biasing condition, right? So we haven't even talked about how we would come up with this IB yet. We'll talk about that in a second. But let's even see if that's really what we would want. So let's say I really did indeed have a constant IB. So now what I want to know is, let's say that just as an example, from whatever reason, the temperature went up. Okay, you went to the Sahara Desert or something and you wanted to use your cell phone. I don't know why, but let's just pretend. Okay, so if temperature went up, what would happen to the characteristics of this amplifier? And let's just pick a few characteristics and let's say, let's see which way they would go. So let's just, I don't know. What do you guys think? What different things would move in which way?
Noise go up.
Okay, that's true. The noise would go up. That's just KT. That's a little bit trickier, but okay, that's true. Actually, the noise would indeed go up. But let's say that, because remember, T is an absolute temperature. So if I go from like 300 Kelvin to 350 Kelvin, that's usually not too bad. But you are right. The noise would go up.
The band gap would change, so VT would increase.
Okay, so you're right. The threshold voltage would go down. Does that matter too much in this particular design?
Well, the bias current in the mirror would increase.
Does it?
Or actually, no, it doesn't.
Okay, bias current in the mirror stays constant, actually, right? So that's in fact, that's the only thing that we've said is indeed constant in this circuit. So that we've kind of forced to be constant. What else would change?
So GM. V star, GM, or whatever.
Okay, GM. What's GM most likely going to do?
It's going to increase.
Yeah, sorry?
It's going to increase.
Increase. If temperature goes up, remember it's constant current. So does V star actually, what's V star sort of related to? Even if I just had like a long channel device.
VGS over VT.
Okay, it's VGS minus VT, which, if I translated that, because remember my current is constant now.
Yeah.
So if I translated GM into current, what's like that relationship?
2ID by the override.
Okay, yeah, no, but so the problem is we're trying to figure out what actually happened to that whole quantity. So just as a reminder, you guys remember something like GM is equal to 2 mu Cox W over L IB? Not that this is correct, but if I have a constant IB and temperature goes up, what's going to happen to GM?
Mobility goes down, so.
Yeah, mobility goes down, right? So remember, the mobility is usually proportional to something like T to the minus 3/2. So actually, GM is going to go down, right? Because we've kept the current constant. And yes, the V star will change, but actually, generally, the V star will increase. Okay? So actually, GM goes down. Okay, what else is going to happen? Let's say, how about the load resistors? What are those going to do?
Depends.
Depend. Okay, that's true, actually. It does depend. Usually what happens, let's say that they're, I don't know, a piece of metal or something like that.
Increase.
Yeah, usually they'll increase, right? Okay, but obviously they probably don't increase the same way. Oops. If we look at the gain bandwidth, what's that going to do?
Reduce.
Yeah, it's going to reduce, right? Because, hey, GM went down, cap probably didn't change, so gain bandwidth goes down. Okay, now, so I just happened to pick temperature over here, but you can imagine I could replace this with process. I could replace this with, I don't know, phase of the moon. Hopefully not, but you never know, right? But basically, do I really want constant current? In other words, for any of the things that we're designing for, does constant current actually guarantee what I care about?
No.
No, right? So it's great, I know what the current is, but that doesn't necessarily give me the amplifier I actually want. This is an example. It doesn't give me a constant gain bandwidth. It doesn't give me even a constant gain, right? Because depending upon what the load resistance did versus what the GM did, the gain could even be shifting, right? So the real trick, again, with all these biasing and reference things is for you to figure out what is the thing you actually want to be constant. Once you know what that is, there's kind of another key step to take. Look at like what's the physical units of essentially that thing that you want to be constant. Okay? If you can't find something that you know is like defined by nature with that physical units, you're going to have a hard time figuring out how to make that thing constant. Okay? Now, the good news is that sometimes things you care about actually don't have any units. They're just set by ratios. That means that if they're set by ratios, you should actually be able to come up with just ratios of any two physical things and control that constant, that quantity. Okay? So as an example, let's say that I wanted to come up with a circuit that would give me constant gain. Okay? So again, I'm just going to repeat my resistively loaded amplifier here. Okay, which of course just looks something like this. And so now what I want to do is, rather than come up with some magic constant bias current, I'm instead going to come up with some bias current that should give me constant gain. Okay? So again, in order to do that, of course, the first thing I have to do is just figure out, well, what actually sets the gain? So, what sets the gain? For this very simple circuit here.
GMRL?
Yeah, it's just GMRL, right? Okay, so just as a reminder, and let's say that there's an IB flowing through here. What is GM set by in this particular circuit?
IB.
Okay, it's IB over something.
Two IB.
Over V star, there we go. In this case, it happens to be IB because half of the bias flows in that branch and half flows in this branch, so it just happens to be IB over V star. Okay? Well, if I look at 1 over GM, that's just V star over IB. Okay? What is the units of that? Yeah, it's a resistor, right? So this kind of says that what I really want to do is somehow make it so that there's some bias current that's related to V star and some resistance, right? In other words, what I really want is, and this is kind of, I really want IB to be equal to GM times V star. Okay? Well, okay, so how could I do something like that? Can you guys come up with a circuit that, given a V star, will give me exactly the right IB? And by the way, I'm giving you I'm giving you one magic trick here. So I'm going to tell you what V star is. So I'm somehow going to give you a V star reference. So can you come up with a circuit that will give me exactly the biasing I want? What do you guys think?
You can put a resistance on the bias side.
Okay. And
And
what
then-
do I put across that resistance?
You can put a this thing. You can put a feedback loop and measure the voltage at the other end and tweak a current source.
Okay, so by the way, what voltage do I want to appear across this resistor? Yeah, I want V star to show up across this resistor, right? Okay, so conceptually at least, the way I can do that is something like, again, I've given you a magic V star reference. I don't know where it came from, but we'll solve that in 1 second. So I can build a feedback loop that forces V star to show up across some resistance over here. Then I can take that same current that caused V star across this RB and mirror it over into my amplifier, right? So now what I should get is that IB is just equal to V star divided by RB, right? Okay, so guess what? If I did that, what would be the gain for this whole circuit? Somebody other than Shiva. So have IB is equal to V star over RB.
RL over RB.
Yeah, it's just RL over RB, right? Because I forced the GM to basically be directly set by 1 over RB. Okay? So again, really the whole point here is, if you know what it is that you want to be constant, figure out what the units of that are, and then see how can you come up with something that will match with those units. In this particular example, since we wanted constant gain, well, remember gain is sort of unitless. So if we just looked at the gain, we said, okay, it's GMRL, that means that somehow either RL or GM have to be ratioed against each other, right? In this particular case, it was easier to force the GM to track with some resistance. Okay? So that's how we ended up with constant gain. Now, obviously, I sort of cheated a little bit, right? Because I gave you this V star to begin with. So somehow, somebody's going to have to come up with that. Well, it's going to turn out, and we'll see how to do this in 1 second, you can actually build a circuit that will use its own V star to create this thing. Okay, now this sounds really recursive and messed up, but trust me, it works. Okay? And we'll see how we do that in 1 second. So just before we do that, there's one sort of quick thing that we need to talk a little bit about, which is usually the number one thing that sort of comes in and messes up whether or not we get the bias we want is the power supply. Okay, and the reason for that is pretty simple, because any circuit we build has to be powered by the power supply somewhere, right? Kind of by definition. So usually the very first thing you kind of care about is just how independent of the supply can you make your bias circuit. So there's a lot of different ways you can do that, but let's just start out with sort of the simplest one we can think of. Okay? So let's just pretend we do something like this. So I have my diode connected device that's acting as a current mirror over here. And then I'm just going to use that, of course, to bias something up. So that's going to be like my I bias at the output over here. And notice what I've done is I've tied this thing just directly through some resistance up to the power supply. Okay? So now the claim here is that if I build this circuit the quote-unquote right way, it'll be at least roughly independent of the supply voltage. Well, okay, so this doesn't really look like it's so independent of the supply voltage, right? But let's see how potentially you could do something like that. So first, just to be sort of clear, what really does set the current in this circuit right here, just sort of conceptually? Okay, so you gave me actually the small signal thing, and we're going to use that in 1 second. I'm saying from a sort of, let's say, quote-unquote, large signal standpoint. So if I told you, for example, that this was, that voltage there, by definition, by the way, is VGS, what's going to set the current through this circuit? Yeah, so the current's just going to be VDD minus VGS divided by RB, right? Okay, so if we want this thing to be sort of independent of VDD, then what is it that we want to have happen?
VGS track VDD?
Yeah, basically you want VGS to just track the VDD, right? Well, so the way you essentially would do that, well, actually, so that would be really good, although unfortunately this particular thing doesn't quite do it. What this one will actually is going to try and do is, there's kind of another way, right? Which is, okay, so let's say that somehow I can tweak this VGS by sizing the transistor or something like that. And instead, what if I just made this RB really big, right? If I make that RB really big, then there should be sort of like, this will be the large signal bias current, right? But now I can look at sort of from a, let's say, quote-unquote, small signal standpoint, how much change in current you would actually get, right? So by the way, just conceptually, if I make RB big, that's kind of like saying I want to make it almost like a current source, right? Because remember, current sources just means high output impedance. So just to be clear, we can sort of go and draw a small signal model to see how much the current would actually change as a function of the VDD. So that would just look something like this. So I have an RB. I basically have a 1 over GM from the diode connected device. And then, of course, over here, let's just call this VB. I'll just have a GM VB, and that will be my I out. Okay? Well, so actually we'll walk through this really quickly, but as you might expect, what you're basically going to end up with is the larger you make that RB relative to GM, the better the supply rejection you'll get. Right? And so just to see that, we can say that VB is just 1 over GM divided by 1 over GM plus RB times VB, right? And so, oops, not times VB, excuse me, times VDD. And so, of course, the I out will just be equal to GM over 1 plus GM RB times VDD. Okay? Kind of makes sense, right? Because if I make the RB really big relative to that GM, the voltage here becomes basically constant. And so the current over there should also be nearly constant. Okay, now, as we've already sort of hinted at, this sort of works, but it's really not great, right? Because what you really wanted was actually somehow that VDD minus VGS would be constant, right? Here, I can kind of make this work, but really the only way I make it work is to make GM really big relative to RB. Excuse me, relative to 1 over RB, of course. Which I can kind of do, but there's only so much kind of room that I have to play with that, right? So instead, what I'd really, really like is somehow to get rid of this, either to get rid of that VDD, or make VGS directly track with that VDD, okay? So actually, what I'm going to claim is the simplest way to do this is make it so that somehow we get rid of this VDD completely. So we make the current depend only on VGS. Okay, so again, this is going to sound sort of recursive, but let's see how we might be able to do that. So let's see how we can sort of improve this thing. So if I want my current to depend only on VGS, then what I'm basically saying is I want to take some resistance right here, and I somehow want VGS to show up on that thing. Okay? Okay, well, so just like we had kind of done before, I can use some sort of amplifier, and I can force, if I somehow had VGS right here, I could basically force VGS to show up on that resistance, right? And by the way, just to be clear, I'm going to be taking my output current from this point right here. Okay, you can do other things, but just assume that this is what I'm going to do. Okay, and you'll see why I did this in 1 second. Okay, so now somehow I've gotten VGS to show up across this resistance. But of course, in order to do it, I needed to know what the hell this VGS was in the first place, right? So I need to generate this VGS somehow. Okay, so now what I'm going to do is I'm just going to redraw this thing slightly. I'm actually just going to build that amplifier, but I'm going to do it in a slightly clever way. Okay, I'm going to build it in a way that actually that amplifier is going to create exactly the VGS that I wanted. Okay? So I still just have, my little sort of Cascode device that has the output current. I have my RB right here. But now to build that amplifier, I'm just going to build it like this. Okay, so it's kind of like the dumbest amplifier you can think of. Just a common source. Okay? So now, why is it that I claim that this thing sort of magically created the VGS that I wanted? How did that happen? What do you guys think? What does this voltage right here have to be equal to? By definition.
VGS.
Yeah, it has to be equal to VGS, right? Because that is exactly VGS, right? So, okay, so I got that to work. Somehow, magically, VGS popped out of this thing. But I still cheated. So what's the cheat that I used right here?
Bias current.
Yeah, I still have a bias current flowing in that amplifier, right? Where the hell is that bias current going to come from? Well, so somebody who knows, how am I going to cheat one more time, but just in a clever way?
Use a mirror.
Yeah, I'm just going to take the thing that is my bias current and feed it back into my amplifier, right? So in other words, just to be clear, this is sort of what we had so far. Right? And so now all I want to do is take the current that I know is going to eventually be flowing at the output and use it to give my amplifier some current. Right? So now this is obviously completely recursive because I needed a VGS there in the first place in order to have some current, and then once I have some current, I get that VGS. But once all that happens, indeed, this thing works. Right? I really will have something that's set only by the VGS, and at least the first order, not by the power supply. Now, what's the problem with sort of all recursive or let's say induction types of proofs? What's like the first thing that you have to do to actually make sure that this works?
Make an assumption.
Yeah, you have to make an assumption about what?
It works. Initial condition.
Yeah, about where it started from, right? So in particular, if this thing happened to start out with 0 current, what would happen?
Stand zero.
Yeah, it's perfectly happy to just sit there, right? So anytime you do one of these things, by the way, this is a real so-called VGS-based reference. Anytime you do one of those things, better be careful that it actually will start the way you want it to. Okay, so we'll see that more in 1 second. We'll actually see sort of an example startup circuit. But with all these sort of reference circuits, just keep in mind, somewhere at the beginning of time, somebody usually needs to kick it.
Oh, but you can't use the current anywhere else though, so what's the
Why not? Just grab that voltage, or grab that voltage, or grab that voltage. Right? All of those are basically just mirrors. Right? So that's the way you actually use it. Okay, so we've kind of talked a little bit about sort of how we do constant gain, how we'd actually sort of would create some even constant current. Although we said that really constant current maybe is not really what we actually want. Maybe we actually want something that changes with, for example, temperature in order to maintain, let's say, gain or something else constant. Turns out it becomes fairly useful to build things that essentially tell you what the temperature actually is. Because sometimes if you know what the temperature is and you can figure out what the dependence of, let's say, I don't know, your gain or your gain bandwidth or let's say your oscillator frequency or whatever it is on that temperature, then it's useful obviously to know what that temperature is. So I think you guys have seen these things many times before, but essentially what people will often then build is a so-called proportional to absolute temperature or PTAT reference. Okay? And in order to get these things, they almost always involve some sort of diode or BJT somewhere. So I'm just going to draw sort of one of the simplest ones first. We'll see sort of how that thing works, and then we'll see how we can actually use it in, let's say, a real CMOS process. So let's just do that real quickly. So I'm going to start this thing off with just a couple of BJTs. Okay, so actually let me draw that a little bit better. Okay, so I have two BJTs like this. I'm going to tie that one up as a mirror. I'm going to say that the emitter area from those two is 1 to m. Okay, and then just because I don't want this whole thing to actually depend on the supply voltage, I'm going to again play my self-biasing trick. Okay, in other words, I'm going to use the current that's flowing through that circuit to basically rebias the other side of the circuit. Okay, so you can kind of see like this whole thing just looks like a loop, right? So whatever the current is here gets mirrored to there. Whatever the current is there gets mirrored back to the same spot. Okay? So the idea, of course, being that the currents in these two should be then the same. Okay? Okay, so let's just sort of do a couple of things really quickly first. So let's say that I just define this right here as being VBE1. Okay? So that's just some base emitter voltage. So now, kind of by definition, what's the voltage that's going to show up there? Yeah, it also has to be VBE1, right? Okay, so if that's VBE1, well, we also know that, of course, from there to there is VBE2, right? So if that's the case, what's the voltage that shows up across that resistor there?
The first one.
Yeah, it's the difference between them, which I'm going to call just delta VBE. Okay? Well, so as we're going to see in 1 second, by using some clever tricks of logarithms and etc., delta VBE is going to turn out to be proportional to temperature. Okay? So the way to see that is just to remind ourselves, let's say I had a BJT or even a diode or something like that. What's the relationship between the current flowing through that BJT, specifically the collector current, and the VBE?
Exponential.
Yeah, it's exponential, right? So there's some, let's say IS1, some nominal current, times e to the VBE, and let's do this as VBE1, over the thermal voltage, KT over Q, right? Okay, so I'm just going to rearrange this slightly, because what I really want is to know something about VBE as a function of the current, okay? So what I'm actually going to say is that this then says that VBE1 is just equal to the thermal voltage times the natural log of IC1 over IS1, okay? So of course, similarly, if I look at the second BJT, then I could say that VBE2 is also the thermal voltage times the natural log of IC2 over IS2, okay? Okay, so now let's look at actually the delta VBE. In other words, VBE1 minus VBE2. Well, remember, whenever you subtract logs, that's like equivalent of doing division inside of the log. So I can actually say that this is equal to VT times the natural log of, and let me just make sure, IC1 over IC2 times IS2 over IS1. Okay? So remember, those IS's, those are like the quote-unquote nominal current. That IS is also proportional to the area of the emitter. Okay? So actually, just as an example, IC1 over IC2, that's the collector currents. So what have I forced that to be? Yeah, I forced that to be the same, right? So IC1 over IC2, that's just 1. Okay, how about IS2 over IS1? What's that going to be? That's just M, right? That's just the ratio of the emitter areas. So now what I get is just VT times natural log of M. Okay, well, that's nice, because remember, VT is just KT over Q. And so indeed, that delta VBE there will be proportional to temperature. Okay? So that's pretty cool. I can actually build something that somehow magically tells me what the temperature is going to be. Okay? And it's not really sensitive to a whole lot of stuff, right? Just by setting that ratio of areas between those emitters, somehow magically temperature's coming out of the picture. So now, by the way, just to make sure things are clear, remember I always said that somehow there had to be something with, the physical units of what you're interested in that would pop out of this thing. So how is it that this delta VBE here is coming out being proportional to temperature? Like, just, physically or fundamentally, why is it that that's the case? What was the key property we're relying on? Yeah, that this thermal voltage is proportional to temperature, and how did that even, how did the thermal voltage come into the picture? What type of element did we have to use? Yeah, we had to use a BJT or a diode, right? Because with a BJT or a diode, the amount of current is exponential and related to that thermal voltage, okay? So again, this is really just a reminder for any of those references, keep in mind what's the fundamental physical thing that's popping out of there that's allowing you to actually build this, okay? So now just really sort of quickly, this is really the basis for all of the sort of proportional to absolute temperature or PTAT references. But there's one minor annoyance, which is in CMOS, you generally don't get to build PNPs. At least you can't build PNPs with the emitter tied to VDD, because usually the only way you can build the PNPs is kind of to like make use of stuff that is not really what the CMOS guys intended. Right? In other words, you just sort of make use of parasitic PNPs that happen to exist in the process. This is an example, the entire substrate is a P, right? you can build an N well, and then you can put a P diffusion in there, which you would have thought was the drain of a PMOS transistor, but for here we're going to use it as the emitter, right? So now this works, but kind of the point is substrate here had better be ground, right? If it's not ground, then kind of the entire rest of the chip that we were futzing with ain't going to work, okay? So what that typically means is that you generally oftentimes have to build PNPs with the collector tied to ground. Okay, and so what you'll actually also typically do then is tie the base to ground and essentially build your circuit with something that sort of looks like this. Okay, so essentially you can almost treat these as two diodes, but basically they're actually PNP transistors. Okay. I can still ratio the areas because that's basically just me changing with the layout, right? So that's pretty easy for me to do, or just repeating the same structure twice. But I just sort of had to flip this whole thing over versus the previous design that we were looking at. So if before everything was sort of referenced at VDD, now this, of course, is VBE1. That's VBE2. And that's where delta VBE is supposed to show up. But in order to make this work, I sort of have to force those two voltages to be equal to each other. Okay? The good news is that's not super complicated to do. And you can do it just as an example with the circuit I've shown here, which is kind of very similar to that previous structure we had looked at. Right? So essentially what you do is you sort of have this Cascode device here. You take the current from that Cascode device, you mirror it over to the other side, shove it back down, and then mirror it back over. Right? So just like before, I'm forcing the current to be the same in the two branches. But by using these stacked cascodes, I'm also forcing these two voltages to be the same. Okay? Does this sort of make sense to everybody? Or? Okay, so now just really briefly, since we'd mentioned it before, and since I've now drawn this a couple times, just like before, if this whole thing starts up with zero current, you're stuck, right? Because it's a positive feedback loop. In other words, if there's zero current there, there's zero current there, it's perfectly happy to just sit there and do nothing. Okay? So just like with the other sort of self-biased circuits, you need to come up with some way of making sure this thing will really start. Now again, there's a bazillion different ways you can build startup circuits, but they all sort of boil down to the same idea. They essentially boil down to, well, detect if there is zero current. If there is zero current, shove some current into the thing. Once you've done that, the thing should start. And then you can just shut yourself off because you know that it won't be stuck at like this metastable point of zero current. Okay? So let's just sort of walk through one example for how something like this might happen. So let's say that this is our, our PTAT circuit right here. And let's say that from whatever reason it started out with zero current, which essentially means that that VGS is 0, and that therefore this thing right here is sitting up at VDD. Right? Because that's kind of the only way that I could have zero current in this circuit. Okay, well, if I have zero current flowing through here, I can detect that by just putting a PMOS transistor biased off of the same gate voltage, right? So if this thing has zero current, then, if the main circuit has zero current, then this PMOS should also have zero current. I can mirror that over to here. And then essentially what I'm doing is just comparing how much current is flowing through this versus how much current would be flowing through this, and this is a PMOS, it's just a little bit hard to see, through this PMOS transistor where I just tied the gate to ground. Okay? So here, if the supply voltage is up and running, there should be some amount of current flowing through there, right? So now, if there was no current flowing through this, what voltage is this going to go up to? Yeah, it's going to be at VDD, right? Which means this NMOS transistor that I added in will turn on. Now, if this thing is turned on, what I basically have is something that looks like this. I have a diode-connected PMOS driving essentially a diode, right? If the supply is there, that'll have current flowing through it. Well, okay. Once current starts flowing through here, now actually there will be some real current flowing through there. I'll mirror that current over to here, and as long as I've set this circuit up with kind of the right ratios, meaning that this current, once the circuit is running, is always way bigger than that current, that will shove this back down to ground.
This will shut off.
I'll shut the switch off, and the whole circuit just sort of sits the way it was supposed to sit. Okay? So again, lots and lots of different ways you can do this. But the key with this one and basically with all of them is just go and detect whether or not any current at all exists. If it doesn't, flip some switch on or add some extra current in and force the thing to actually start. Okay? Now, by the way, just to be clear, why did I do this whole complicated procedure over here rather than just something like, let's say, just always shove some current into that branch right there? You know, why didn't I just like put a PMOS device there and force some current to flow through there? Why did I want to avoid that?
Screws up our.
Bad.
I heard a few things. Screws up our biasing. What else did you say?
Because that would be bad.
That would be, okay, yes. I mean, I guess if I asked the question, it would have to be bad. But yeah, it basically screws up the bias, right? Because if I always did this, then now I have some asymmetry in the circuit, right? And I won't get exactly the characteristics that I wanted before. Now, even with this, it's not exactly perfect because there's always a little bit of leakage through that transistor. But you can make that really, really small in comparison to the actual current that's flowing through here, right? There's actually one other sort of interesting question that we should go over before we finish for today. So, back when I first built this structure like this, how did I decide that I want the diode connection over here on this side and the diode connection over there on that side? How did I decide that? Why did I put it this way versus the other way? And by the other way, just to be clear, I mean, why didn't I try and do something like, let's say, that? Yeah?
Because the top mirrors, you have to sense your reference. So you have to sense that using the top mirror.
Okay, you're absolutely right, but let's just be, really clear. So you said you have to set your reference. Why did we decide that this side right here is the reference? What's magic about that side versus the other side?
That's a resistor.
Okay, there is a resistor there. Why is that important? You're actually right. Now we just have to figure out why. What's that, Dan?
The current's delta VBE over R.
Okay, so you're right. The current is indeed delta VBE over R. That's kind of the only thing that's defining the current. So you can sort of wave your hands a little bit and just argue, okay, since the current has to be defined by delta VBE over R, what we want to make sure is that we mirror the current from here to there, because we want to make sure that this other current is forced to be delta VBE over R, and not the other way around. Now, why is that? Okay, I agree that the current is supposed to be delta VB over R, but I think I could wave my hands and argue that if I flipped the mirrors, I would still get that, at least if I wasn't careful about solving a few things. So, what's the problem with the other configuration? Or actually, why did I even choose this configuration in the first place?
The other one is a positive feedback with gain.
There we go. Right, so remember the whole trick here is I've actually got both positive feedback and negative feedback, right? Because if you follow the loop one way, you get positive feedback. If you follow the loop the other way, you get negative feedback. So the real trick here is that I wanted to make sure, by tying it this way, this was the only way to guarantee that the negative feedback is larger than the positive feedback. So now, by the way, how did I get to that? How can I see that, basically the gain, let's say, to this point would be larger than the gain to that point? Why might that be? What would the gains be sort of related to if I looked in this loop right here? Yeah, there's a GM in there. And what else? Let's just say let's just do something really simple. So let's say I break the loop. Can I just inject a little test voltage right there? What would set the gain from this point to that point?
Degenerated by R.
Yeah, it's degenerated by R, right? So you'd get something like the GM of the device over 1 plus GM. Now, by the way, is it just the R, or is there something else there too?
Auto.
What's that? Don't worry about ROs, by the way.
The emitter resistance.
Yeah, there we go. It'd be something like the resistance of the diode, right? What is that resistance, by the way? Is it big or small? Small, right? So we can kind of usually ignore that. How about on this side? Do I have anything making that resistance large?
No.
No, right? I just have the diode, right? So if you walk through the loop from this side versus if you did the same thing on that side, what you'll see is that because this one is not degenerated very heavily, you'll find out this gain would be large, whereas this gain, because it's degenerated, would be small. So it turns out you have to tie the loop this way to make sure that the negative feedback would actually win over the positive feedback. Okay? This make sense to everybody, or? Okay, so just one last sort of quick thing before we break for today. Once you've built a PTAT reference, kind of like we've been talking about, and again, paying attention to which way things should go, you can actually also build something that has a constant voltage. So, by the way, I'm assuming, how many of you guys have seen band gap voltage references before? Okay, good. So, general idea is very simple. You take the thing that's proportional to absolute temperature, you somehow add it to a VBE, which VBE turns out to drop by about 2 millivolts per degree C. If you add these two things together, basically the delta VBE does something like that. The VBE does something like this. If you add those two together with exactly the right coefficients, you can get a voltage that turns out to be related to the band gap of silicon that's basically flat. Okay, now again, the key point here is that there had to be some physical thing that was actually, that you could measure that was allowing you to build that constant voltage. Because otherwise, if you can't tell me what's the physical thing that was acting as your reference, I don't believe your reference is really a reference. Okay?
Got the silicon changes temperature.
Ah, indeed it does. So are band gap voltages really constant? No, they're not. Right? They actually do shift a little bit. Now, there's all kinds of tricks people have come up with of so-called curvature correction and etc. that basically try and counter that. But none of them are perfect. Because again, there has to be some fundamental physical thing that's there that you can rely on to say, okay, I'm pinned to that thing. Okay, so we'll finish up with this next time. So I'll see you guys then.